Okay, dear students, welcome to this video. In this video, we are going to learn about energy in simple harmonic motion. So, for the old syllabus students, this topic was some part of it was included in topic 4, which was SL level, and only the graph was there. So, it was only like you need to know that this is the kinetic energy, this is the potential energy in blue, and so where the kinetic energy is maximum and where the potential energy is maximum, the sum total remains the same as the total energy, nothing more than that. We would be doing that, but in the topic 9.1, when which is the HL topic, we have to delve deeper and there will be more formulas that you must be knowing. In the new syllabus, there is no such kind of segregation. Everything is uh, created into one bundle only. So even I'm creating videos in one bundle like that. So it will be better if you understand this thing properly. And the students, those who are in SL, they can when I switch to the HL mode or the formulas, I will specify this is HL and this is SL. Okay, so first of all, the graph of energy in simple harmonic motion is in front of you. This is how it looks like. But how can you derive it, first of all? Now, a part of it, like the derivation that I'm going to give you, it belongs to the HL. Okay, so let me do it now. So let us say that the displacement is given by x naught cos omega t. So the velocity will be like we would be differentiating it, and this is the expression that you will find for the velocity. Okay, here we want to relate the potential energy with x, like this is the x displacement, a is the amplitude, the maximum displacement, and you want to relate the kinetic energy also with the x, and only then you would be getting these graphs. But in these expressions you can clearly see x and v, they are related with the time t rather than the x. So we want to create those expressions. Let us go for the potential energy first of all. So potential energy is easy. We know that the formula is given by half kx square. As I told you in my previous videos, that whenever we talk about simple harmonic motion, we have to imagine the spring mass system always. And in spring mass system, there is only elastic potential energy, which is given by half kx square, and that is why the expression. It means that the graph of the potential energy with respect to x is going to be a positive parabola. I'm calling it positive because it is upside there, like that, a concave up. So it is positive parabola, I can say. Yes, positive parabola means like somewhat like this. So it is y is equal to x square situation. So I'm just calling it as positive parabola. So formula is in front of you, and indeed this formula is one of the most simple formula for the simple harmonic motions, but it is the most effective formula that we are ever going to use in simple harmonic. So whatever motion that, whatever energy they want to consider, they want to consider potential energy or the kinetic energy or the total energy or whatever, this is the formula that we will be looking forward to. I will be telling you like which formulas are useless and you are not going to do that. Do those formulas, I will show you. So first thing is clear, this is the potential energy, which is a parabola, and blue colored graph belongs to the potential energy. What are the things that can be learned from this? Point number one, the potential energy is zero at the equilibrium position when x is zero. And the potential energy is maximum when the displacement is maximum, which is equal to amplitude. So I can say that x is equal to a, that is the amplitude here. So when the body is reaching the amplitude, the spring is in the maximum stretched condition, and so the energy is maximum. So this is the maximum energy, which is half ka square. Okay, and x is equal to a, that is the amplitude. This is what we need to understand as of now. Now we are moving into the expression for the kinetic energy, and let's see. Kinetic energy, the universal formula for this is half mv square, and we have the expression for the velocity also, but we don't want to get into this because this is time. Okay, so kinetic energy is half mv square, and so what can we do here? We want to use the expression for the time of in the terms of x. Okay, so there is another formula, which is velocity is equal to omega x naught square minus x square square root. You might remember we just did now in couple of earlier videos. This is the expression for the velocity in terms of x. We directly substitute this value here. And so we are getting the formula as this. V square, it becomes omega square. This becomes x naught square minus x square. This is a very dicey formula now. Now this is the kinetic energy in the terms of x. And we can clearly see that the graph of the kinetic energy will be directly proportional to negative x square. So we can call it negative parabola. Negative parabola means that it will be upside down, and so the parabola in red relates to the kinetic energy. Clear? Now, it is a parabola this is like in front of you. Mathematically, we have proved now. So this is the parabola. What are the points to be noted here? Kinetic energy is equal to 0 at extreme position. So when x is equal to plus minus a, that is the amplitude, x naught is the amplitude in this equation, so the kinetic energy will become equal to 0. And kinetic energy is found to be maximum if x is at equilibrium position. This is the equilibrium position, and you see kinetic energy is max here. First of all, this is what we need to understand. Okay, not very humongous mathematics, isn't it? So if you're SL student, even then you can just keep watching the video. Whatever you retain, it is good. No need to give special emphasis to retain things. Okay, after this, another point that can be noted here, it is that what is the sum total of this? What is the sum total of this? Now the sum total, so it will be equal to potential energy plus kinetic energy. So this is half k amplitude, I'm just writing it as a now, and this kinetic energy, which is half m omega square into x naught square minus x square. X naught is the amplitude, so I can write it as a, not to confuse within the variables, be very careful. So k is equal to m omega square. From where I can say that? Because I know that omega is equal to square root of k by m. We did it when we were finding the time expression for the spring mass system. You can watch that video again. This omega value, like k is equal to m omega square, can be substituted here, or this can be written as k. So it will become half k a square plus half k a square. Sorry, this is not the amplitude. This is not the amplitude. This is x only. This is x. I'm talking about this formula, no? Instantaneous potential energy. So it is x. I mistakenly wrote it like that. Half k x squared. This and this gets cancelled out. So what do you get? Half k a square. What does it mean? It means that the total energy, if we talk about, half is constant, k is the spring constant, it is constant, and the amplitude is also a, which is constant value. So the total energy is constant there. It means that the sum total is shown here. You can see this is the total energy. So total energy is constant at all the points. Why? Because when we are adding these, the total energy becomes constant. So you can just say that at any position, if you find the values, these two values, when you add them, you get the total energy. So for the SL students, I tell you, like when you there might be a question like the total energy is like kind of 80 joules. What is the potential energy at so and so point, and what is the kinetic energy at so and so point? So if this is 20, this is 60, this will be 80, like that. And each and every point, this thing is going to happen, even at this point. Yes. So another point to be noted here is that the total energy is equal to a constant value. Now it means that the total energy is equal to max potential energy, which is going to occur at the extreme positions, and it is equal to max kinetic energies at this point, which is shown here. So this is the expression. You need to remember it. It's a very important expression. I have seen many questions in IB where they do ask about the total energy, but they do not tell you what is the total energy. Instead, you have to find the maximum potential energy to find the total energy. Okay, you have to find the maximum potential energy to say what is the total energy. It is like that. So this is a very important expression. Now, after this, now I'm going to tell you the end point of this video, like the gist here. What is happening is we have one expression for the instantaneous potential energy, which is half kx square, one for the kinetic energy, which is coming out to be half k x naught square minus x square, which can literally be translated into total energy minus potential energy, isn't it? Which can be written like this. Absolutely. So, overall, what we want to say is that there is no expression for the kinetic energy in terms of x. Why you want to learn another expression for the kinetic energy? That is not required. We will find potential energy in every question. In every question, we will find the potential energy. The total energy will be equal to half k amplitude square. We will find that, and then we subtract them to find the kinetic energy. No need to use any direct formulation for kinetic energy. It is given in your data booklet, but it is highly misleading. I would be talking about that in the next video. So for the kinetic energy, do not use direct formula. Why I am saying that? Because that is highly erroneous, and repeatedly I have seen students commit some or the other mistake. So if you are using the formula for the kinetic energy, which is given in your data booklet, in the previous syllabus it is given in topic 9, you are definitely going to uh, like going to do some mistake there in the calculation, and you are not going to get the correct answer. So do not use that expression which is given in your data booklet. Okay, so with this, this thing is over, and I would be moving into the next types of graphs for the kinetic energies and the potential energy. Thanks for watching. See you in the next video. Bye.